My name is Tom McCoy, and I will be discussing universal linguistic inductive biases via meta-learning, which is a collaboration with Aaron Grant, Paul Swansky, Tom Griffiths, and Tolmanson. Language acquisition involves an interplay between data in the language and the learner's inductive biases, which are the factors that affect how the learner will generalize beyond the data. As an example of an inductive bias, consider this mapping. If GBG goes to ga-ba-ga and ZZ goes to za-za, what should TRV go to? You probably answered ta-ra-ba, but other answers are possible. For instance, the examples shown here are also consistent with the rule that requires you to reverse the input elements, in which case the answer would be va-ra-ta. If you answer ta-ra-ba instead of va-ra-ta, it suggests that you have an inductive bias for preserving the input order. The question motivating this work is, how can we computationally model the interplay between data and inductive biases? One popular approach is to use symbolic probabilistic models, such as most Bayesian approaches, which are suitable for targeted investigations involving carefully controlled data, but they typically require a large number of theoretical commitments to be made, which can make these models too restrictive to handle more realistic data. On the other hand, neural network models are powerful enough to handle realistic data, but they are under-constrained, which means that they usually require huge amounts of data to learn anything useful, and they usually generalize poorly to novel types of examples. These shortcomings could be fixed by building in additional inductive biases to help constrain the learning of the neural networks. However, it is typically difficult to do so. In this work, we introduce a framework for giving linguistic inductive biases to a neural network, in the hope that this will combine the power of neural networks with the controlled inductive biases of Bayesian approaches. Our framework has 4 steps. First, we define the inductive biases that we wish to impart, then we translate those biases into a space of languages. Next, we have a model meta-learn from languages drawn from that space. I will define meta-learning in more detail soon, but briefly what this does is it gives our model the ability to learn any language from the space of languages from a small number of examples. Our hope is that by giving our model this ability, we will also impart the set of inductive biases that was used to define the space of languages. To see whether that hope was borne out, the final step is to analyze our model to see if it has meta-learned the intended biases. This framework is very general and could be applied to any aspect of language, from phonetics to semantics. Here we apply it to one particular case study in phonology, namely syllable structure. To preview our results, we find that meta-learning successfully imparts all of our target inductive biases. For the rest of the talk, I will now walk through the 4 steps of our framework as they apply to this case study. To do this, we first need to define the inductive biases we wish to impart, which we will do by adopting the account of syllable structure as it is handled in optimality theory. Let me stress that our framework does not inherently depend on optimality theory. This is just the example we chose to illustrate it. In optimality theory, each word has an underlying form, which is a sequence of phonemes, such as KTA, and a surface form, which is a sequence of syllables, such as ka-ta. Languages differ in how the underlying form is transformed to the surface form. One language might turn KTA into ka-ta, while another might turn it into ka. The pattern is governed using 4 constraints. Here I will define the constraints using 3 example input-output mappings, where the input is always BIP, but the output could be bib, bip-ha, or bip. The first constraint, onset, says that every syllable should begin with a consonant. All 3 examples satisfy this constraint because all of their syllables begin with consonants. Next, no coda says that no syllable should end with a consonant. Our third example violates this constraint because its syllable ends with a consonant P. No insertion says that nothing should be inserted into the input, which is violated by the second example, which has inserted an A, and no deletion says that nothing should be deleted from the input, which is violated by the first example, which has deleted the P. These constraints are not arbitrary. They are motivated by linguistic universals. For instance, across languages, there's a preference for syllables that begin with consonants but do not end with consonants, motivating the onset and no coda constraints. Sometimes constraints conflict with each other. Here, the no coda constraint would push a language to choose one of the first 2 mappings rather than the third one, which violates the constraint. However, if you were to choose one of those first 2 examples, you would have to violate either no insertion or no deletion. So here, no coda conflicts with no insertion and no deletion. Such conflicts are resolved with a ranking of the constraints. For example, if we rank the constraints in the order shown here, with onset ranked highest, then no coda, then no insertion, then no deletion, then the first mapping would be the one that the language would choose because it is the one with the least serious constraint violations, since the only constraint it violates is the lowest ranked one, no deletion. However, if we swapped the order of no deletion and no coda, now the third example would be the one that wins, because now it is the one with the least serious violation. So this example shows how differences in rankings explain why languages differ. And overall, our goal is going to be to give our model a set of inductive biases that encodes knowledge of this optimality theory framing. To do this, we now need to translate those inductive biases into a space of languages. We will define an individual language as follows. First, we must select the set of consonants that can appear in the language and the set of vowels. Next, we must choose which consonant and which vowel will be used for insertion when we need to insert a segment. And finally, we must choose the constraint ranking that will govern the input-output mappings. Our overall space of languages can then be defined simply as the set of all languages that can be generated in this way. Now we must have a model meta-learn from languages drawn from that space. The model we will use is a sequence-to-sequence neural network, which reads in its input one symbol at a time and then generates its output one symbol at a time. In our case, the input is a word's underlying form and the output is the word's surface form. Before I define what meta-learning is, I'm going to first define what standard learning is. So our model, like all neural networks, is governed by a large number of numerical parameters, which we can visualize as this parameter space. Hopefully, there will be some range of values for these parameters that would enable the model to perform input-output mappings in a given language with high accuracy. We can visualize that range of parameter values as a region in parameter space. Unfortunately, we don't know where this region is. So the standard approach is to first initialize the model's parameters at some randomly selected set of values, and to then train the model on a large number of examples from the language, where after each example, the model's parameters will be adjusted slightly, such that if it were to encounter the same example again, it would now get closer to the correct answer. And after performing many such adjustments, the model's parameters will end up in a position where it can now perform input-output mappings very well in this language. So in standard learning, the goal was to have the model learn one particular language. In meta-learning, by contrast, the goal is to give the model the ability to learn any language in the space of languages. For this reason, it's sometimes called learning to learn. The variant of meta-learning that we use is MAML, which learns a parameter initialization that supports rapid learning. To break that down in more detail, we once again will be working in the model's parameter space. But now instead of having just one language, we have a whole space of possible languages. Just like before, we will initialize the model's parameters at some random point, but now we will sample one language from the space of languages and train the model on a small number of examples from that language using standard learning. After the model has finished training on that small number of examples, we will then figure out how we could adjust the model's initialization such that if we were to train the model again on the same language, it would do better on the language at the end of training, and then adjust the initialization accordingly. Then we sample another language from the space, train the model on a small number of examples, and then adjust its initialization once more, such that if it saw this language again, it would do better on it. And we keep performing more steps of this meta-learning process until eventually, hopefully, the model's parameter initialization will end up at a position from which it can readily acquire any language in our space of languages. So in some sense, MAML gives us the best of both worlds when it comes to modeling inductive biases. First, under some circumstances, MAML can be interpreted as learning the prior in a Bayesian model. Yet the model that is given this prior is a neural network. So this allows us to combine the strengths of Bayesian models and neural networks. An important aspect of MAML is that it encodes the prior, or the inductive biases, in the model's parameter initialization. Whereas many other approaches for giving inductive biases to neural networks instead focus on encoding the biases in the model architecture, potentially augmented with knowledge that the model has access to outside of the network. In our experiments, we compare a model initialized with MAML to a randomly initialized model. Crucially, these models are identical in their architectural structure, but differ only in how their parameters were initialized. This framing instantiates one classic definition of universal grammar from linguistics as the initial state of the language learned. Okay, so now that our model has meta-learned from our space of languages, we now need to analyze it to see if it has meta-learned the intended biases. To get an initial sense of how the model is performing, we're going to use some screenshots from a demo of our models that we posted online. So here's what the demo looks like, and I'm now going to walk through the different components of the demo. In this example, the language that we want our model to learn has the restriction that the output syllables must all be of the form consonant vowel. Sometimes that's easy to satisfy because the input already satisfies it, but sometimes the model needs to insert the consonant D or the vowel E or both. So basically what the model needs to learn here is first, which types of syllables are allowed, and second, which consonant and vowel does it need to insert on occasion to satisfy that syllable structure constraint. We'll be looking at two different models, a model initialized with meta-learning and a randomly initialized model. We can see that even before any training on this language has occurred, the meta-initialized model is already getting one of the examples right. And this makes sense because in the optimality theory account that we've adopted and that the model meta-learned from, No matter which language you look at, an input of the form consonant vowel will always map to an output of the form consonant vowel. So it's good that the model seems to have learned that universal fact about languages such that it knows what the output should be in such a case, even without any training in the language. However, for the rest of the examples, neither model is getting the right answer, so in order to actually learn the full language, we now need to train our models on some examples from the language. So after we train on one example, you can see that the model's predicted outputs have changed, but they're still getting most of them wrong. Now we've trained on 2 examples, 3, 4, 5, 6, 7. Okay, now after 7 examples, the meta-initialized model is getting several more examples correct, but still not all of them. Now 8, 9, 10, 11. Now, after seeing only 11 examples, the meta-initialized model is scoring perfectly on its test set, whereas the randomly initialized model is still generating gibberish and getting no examples correct. And in fact, even though the meta-initialized model only needed 11 examples, the randomly initialized model typically needs a few thousand examples to learn language properly. So this rapid learning gives indirect evidence that our model has learned the set of inductive biases that we wanted. However, to get a more direct evaluation, we're going to now perform targeted tests for each of our 6 intended biases that we wanted to impart. In this talk, I'm only going to talk about 2 of the 6. You can see our paper for the other 4. The first bias I'll discuss is based on the set of constraints. Recall that our syllable structure framing uses the constraints onset and no coda, which say that each syllable should begin with a consonant but should not end with a consonant. One can imagine 2 alternate constraints of no onset and coda, which would say that every syllable should not start with a consonant but should end with a consonant. So here we analyze whether our model has meta-learned a bias for the correct constraints, onset and no coda, over the incorrect constraints, no onset and coda, which we do by testing whether it is easier for our model to learn languages defined with onset and no coda than languages defined with no onset and coda, where ease of learning is quantified by the number of examples that are required to reach 95% accuracy on the language. And here are the results, where each bar is an average over 100 languages. You can see that our model requires far fewer examples to learn a language defined with the correct set of constraints than to learn a language defined with the incorrect set of constraints, and that it needs an intermediate number of examples when the language is defined with 1 correct constraint and 1 incorrect constraint. This shows that our model has meta-learned a bias for the correct set of constraints over the incorrect set of constraints. The next bias we look at is based on implicational universals. Under the optimality theory account that we use, the presence of certain mappings in a language implies the presence of certain other mappings. For instance, if a language maps an input of the form vowel consonant to an output of a single vowel, it's also guaranteed to map a consonant vowel consonant input to consonant vowel. Such implications are called implicational universals. So we now test whether our model has a bias for such implications. We do this by training the model on one particular language using only inputs of one type, such as vowel consonant, and then test it on inputs of a withheld type, which forms the second half of an implicational universal, to see whether the model is able to leverage that implicational universal to generalize from one input type to the other. And here are the results. You can see that both types of model, whether initialized with meta-learning or randomly, can perform well on the type of example they were trained on, but only the meta-learning initialized model is able to generalize well to the novel example type, indicating that meta-learning has imparted inductive biases consistent with these implicational universals. To conclude, meta-learning with MAML successfully imparted all of the inductive biases that we specified, which shows that biases previously framed in symbolic terms can be reframed in the context of neural networks, to facilitate cognitive modeling that combines the power of neural networks with the controlled inductive biases of symbolic approaches. One important aspect of our framework is that it imparts soft biases, not hard constraints. For example, languages that were unnatural in the optimality theory framing were harder for our models to learn, but not impossible to learn. This softness can be viewed as a strength or as a weakness. It's a weakness in that, at least under some views of optimality theory, the unnatural languages should be truly unlearnable. However, it can also be viewed as a strength because many believe that language universals are better viewed as statistical tendencies rather than hard constraints. We hope that this approach can be used to test cognitive theories. For example, you can use it to create a model that has some bias hypothesized to play a role in language acquisition to test whether that bias actually has the hypothesized effects on learning. In the example we talked about in this talk, we use meta-learning to impart a set of pre-specified biases using constructed data. An alternate way to use our approach would be to have a model meta-learn from naturally occurring data and then analyze the model to see what biases it has meta-learned to gain insight into the pressures that shape the data. You can see our paper for several more experiments about other inductive biases, including some more abstract biases and also generalization to novel symbols and a novel length, And you can also see our demo that was used earlier as an example at the project website.